Now let's look at the last step in the modeling process for multiple linear regression, and that's how do you evaluate the model. As a reminder, here's where we've gotten to so far, and again, I'm including our notation that we've used here, as well as the linear algebra notation. So this is out of the scope, but just so you can see. And this is the actual linear algebra solution that's going on behind the scenes in scikit-learn. So before we go into metrics, I want to point out and compare this model with what we've done so far. We've done constant models, we've done simple linear regression, now we're looking at ordinary least squares. In each of these cases, we have closed form solutions, as in I can tell you here is the actual best fit parameter, or your best fit, theta knots parameters for your model. Here we have to use vector notation or matrix notation, but it's the same idea as what we were doing here, just extended, generalized. What's interesting is all of the models that we have that are using mean squared error actually do have unique solutions. And in our ordinary least squares case, I will have a unique solution if all of our features are what are called linearly independent, and if your number of data points is much greater than your number of features. And that's going to be very useful to have the ability to have a unique solution. We will look at what happens in cases when we don't have linear independence, and we'll see how you can test whether your features are linearly independent. But just to know that this modeling framework does have a nice closed form solution, and a unique one in some cases, is very helpful, because this is a very robust modeling framework. Now, given that, let's talk about how we could compare different OLS models. So maybe I've chosen different features, or I've added multiple features to one model versus another. What are some ways that we can decide which model is best? So the first thing we're going to do is the same thing we did with simple linear regression, and that's to look at the residuals. And in simple linear regression, I had us do this. I either plotted the residuals versus your single feature, or I started showing you that's going to be the same plot visually as the residuals versus your predicted outputs. And that was really to set you up for this, because in multiple linear regression, we are going to plot the residuals versus your predicted values of y, just because that way we can do it all in one plot like this. We're going to use the same interpretation as before. A good residual plot shows no pattern. It's going to have similar vertical spread throughout the entire plot. So those are key things we're looking for. And again, if you don't have that, it's just signaling to you that you can probably improve your model somehow. If this had a lot of patterns in it also, then you could start plotting the residuals versus different features. So maybe you used 2 or 3 features in this multiple linear regression model. You could do 2 or 3 plots of the residuals versus each of those features to really see where the patterns were showing up. But this is a really good starting point. In addition to visualizing residual plots, we do have the generalization of these 2 metrics that we used for simple linear regression. So we're going to still calculate RMSE for our multiple linear regression models. And again, the lower the better. And then we are going to calculate a generalization of this correlation coefficient. In particular, we're going to calculate this squared, but in the context for multiple linear regression, we're going to define that as our variance of your predicted values divided by your variance of your original values. And we showed when we first defined this metric in our simple linear regression video, I mentioned that that was equivalent to this ratio, which is why we can generalize it this way here. And if we dive into this a little bit more, this coefficient of determination is going to range from 0 to 1. Again, think of it as the proportion of variance the model explains. So the closer to 1 this is, the better. And it is a really nice generalization of this little r squared, because if you have OLS with an intercept term, like this, then this multiple R squared is equal to the square of the correlation between your original data Y values and your predicted Y values. And for simple linear regression, this is exactly equal to the correlation squared. So it's a nice generalization. The downside of using this metric is as you add more features, the R squared is generally going to increase. And we have to be wary because adding more features doesn't always make a better model. And we'll see that in an upcoming video when we talk about overfitting. But a way around that, or a way to kind of adjust for overfitting and adjust for this issue when looking at our R squared, is to use what's called the adjusted multiple R squared. And what this does is add a little penalty for each time you add a feature or a predictor. And this makes it a little bit more useful when comparing models with different numbers of features. And so we will be using this adjusted R squared when we look between models that have different numbers of features. So let's actually pop over to the notebook and examine this for our hybrid data set. So we're back in the OLS notebook, and if you recall, we had decided to fit a model of this form, where we had acceleration as one of the features and miles per gallon as the other, and this is to predict MSRP. And we are going to contrast this model. So we fit this, but I want to contrast it with our simple linear regression model that we did above. And this is all from the previous video, where we had an RMSE of around 15,000 and an R squared around 0.48. So those were our baseline values. And now we're going to look at these same ideas. And also here was our residuals. Oops, those are a little bit shifted here. Let me clear this. There we go. These were our residuals for our first model. Then when we added more features, we ended up with this plane as our model right here. And now let's look at some of these metrics. So first we can look at RMSE, and we're going to see this one, it's gone down. Now it's 14,000, so it's moving in the right direction. We're now going to look at our multiple R squared, and it's gone up from, remember our other one was around 0.48. So now we're getting an increase, which is great. But as I mentioned, it's always going to go up when you add new features, as long as they're independent features. So you do want to do an adjusted multiple R squared, which I'm going to do in just a minute here. Just to point out, there is a built-in method to calculate your multiple R squared. You just use .score. So that's equivalent. There isn't a built-in method to do the adjusted multiple R squared, so I just had to do that manually here. And so you can see, right, we get a small penalty. It's a little bit smaller. Instead of 0.527, it's 0.521 basically, but it's still higher than our simple linear regression model. So this is looking better. Now, I also can analyze my residuals. And so here is a plot of the residuals. And I still see this kind of trend happening this way, which is a little disconcerting. So my residuals are still not great, which is telling me I probably could do better in this model. But again, this is an improvement from just the simple linear regression model. So what do we do next? We've added another feature. This is where we are now going to look at what's called feature engineering. Thinking of what kinds of transformations could we do to the features? Should we add, for example, like a qualitative feature instead of just the quantitative? And that's the topic of the next video. So we're going to continue revisiting this data in the next video as we move on to feature engineering.